Hello, it is June 3rd. Today's lesson is for June 3rd, and what we're going to be doing is reviewing the solving of nonlinear systems of equations. So, uh, I guess last week we reviewed and learned about solving systems of equations or using systems of equations and with three variables. So that is something that we did and the process that we use to solve for systems of equations with three variables. And what we're going to do today is we're going to use graphing to do that, to do the same thing. Now, please skip the first page. I'll talk about this when I come back, but this talks about a circle. So scroll down or go down to the next page. And what I'd like you to do is focus on 1 through 6 primarily, and then if you have time, 7 and the rest of it. But the main thing is this. So I'm going to go ahead and work one, maybe two of them with you. And then I'll let you do the rest and just do the best you can. You can work together and then we can certainly go over them when I come back tomorrow. Okay, so again, now we're going to just basically by graphing and then plugging in to verify the solution. So if we look at the first one, we have two equations. We have this equation here. So we're looking for an XY value that satisfies both equations, and graphically we can see where that the intersection is. So in a real simple situation like this, right, you got a line like that and maybe a line like that. Well, there's one specific point, right, if you graph two linear equations or any equation where they're going to have the same x and the same y solution at the same time, but only at that time, right? So whatever the x is at that point, they both have the same x and the same y. Now, if I did any other x, like say x2, for example, this first line would have a solution for y right there, but the second line would be right there, right? So again, where they intersect represents a situation where they both have the same x and y at the same time. That's why they call it simultaneous equations. So we're going to graph to try to find where that point of intersection is, and we know that they'll have the same x and y solution at that time. Now, what do we have? We have a log equation first, and we have an equation with just an x and a y. And I don't know if you remember, but that's a linear equation, right? There's no exponents, there's no logs. It would be a linear equation. So one way you can always do it by graphing is just make yourself a table, right? And then pick really simple, easy values. So I'm going to start with this one over here, okay? So I like to start with 0, my favorite number to plug in, right? So I'm going to make a 0 for that. And then this would be 0 plus 2y equals 6. Divide both sides by 2. Y would be 3. So then I'd go 0, 3 would be 1 point for the first equation, right? And then I'd say, what's another simple value? Well, if it is, I'd like to make y 0. So if y is 0, that would mean that x plus 0 equals 6. So x would be 6. So when y is 0, x is 6. Okay. Now, since it's a linear equation, at that point, I can pretty much just draw a nice line. Although I may want to do one more point, maybe somewhere in the middle, like a 3. But the point is, if you draw, you can use a ruler if you want, a nice long line like that, you're going to basically find where it goes. And then if we get a little bit closer to the other one intersecting, we can maybe confirm it. Okay, so now we can do the same thing with the log. The log might be a little bit trickier, right? But we just learned about it. So here we have negative log 3x minus 1. So our goal is to think about what value, when you take 3 and raise it to something, what would the exponent, right, be? Because this is the base, right? This is the result. The x minus 1 is in the result spot. And this is the exponent. So my thought is, let's use a really simple number. I think if the exponent is 0, right? So if the exponent is 0, then then that means that the result's always going to be 1. And so maybe it's even easier to write it out like this, like 3 to the, oops, where's my pen? There we go. 3 to the power of 0 is equal to 1, right? So that means we need to get the parentheses needs to be equal to 1, right? 3 or x minus 1 is equal to 1. Both sides, you add 1, x is equal to 2, okay? So when x is equal to 2, now, by the way, that is just this part of the equation, okay? So this part of the equation is going to be equal to, the whole thing together is equal to 0, right? Okay, that's the result. Not the result, but the exponent is 0 for this one, right? That's the exponent. But then you got to add 2 to it. So 0 plus 2 is 2 there, and I put x in the wrong spot. Actually, no, I didn't. So when x is 2, y is 2. Oh my goodness gracious, check that out. It looks like we got lucky. And we see, and I can put this one in red, that our very first point just turns out to look like it's the point of intersection. So you may have to do it a few times to do that. But as teachers, we're not going to make it really crazy where there's decimals. They're all going to be nice, easy whole numbers. But you may want to grab just one other point. Let's just pick one other point for its log. Now, you probably also are going to remember that ideally from the transformations, you can see, hey, there's a negative in front, there's a reflection, there's a shift, right, to the right by 1, and then there's a vertical translation up by 2. But let's just put in another number. What would be another good number to do? Well, that would be if we had 3 to the power of 1 is easy equals 3, right? Again, that's for the whole thing. That's for the result. So I'd go x minus 1 equals 3. So x would have to be 4, right? So, okay. Now keep in mind, this is negative, so it's actually going to end up being negative 1. The whole thing would be 1 if it was 3. And since it's negative 1. So negative 1 plus 2 is 1. Okay, so y is 1, x is 4. Okay, so, but again, I'm thinking that the correct answer is going to be 2, 2. So if I already know 2 worked for the log one, so if I plug it in here, will it work? So x is 2 plus 2 times 2 for the y part. That's 2 plus 4. That checks. So basically the answer would be 2, 2. Now, at the bottom of the page, you'll see the answers. The answers, whoops, there we go. Number 1, let's scroll down, and we get 2, 2, but also 4, 1. Okay, so by the way, that did look like there was more than one answer, right? Okay, so that is something that you need to look for on these here. There was one answer like that, right? Okay. Now, one other thing that I did, as you can see, that's been added is to give you an idea that there's going to be a good opportunity for, or good chance there's going to be more than one point of intersection. I think what you can do is use what we learned about graphing transformations as a good review, thinking about, what is the structure of this going to look like? I plugged in points to figure out 2 points for the log, and I stumbled across, luckily, I guess, 2 points that were points of intersection. But how could I have an idea that it's going to probably intersect around here and here, or somewhere in that range? Because that can help you to figure out what values to try, right? So, you can think about, what would a log 3 look like? Well, it would start at, the starting point is always that for a log, right? And then since it's a base of 3, the next point would be 3, 1. That's the starting point. But then it has a negative in the x-axis, right, a reflection, but the first one stays there because it's times 0, right? The y value is 0, so that doesn't go anywhere. Although this one would be down here, okay? So it's going to be down 1, 2 over. But then it moves to the right. Both points move to the right, so I can go with the starting point real quick right there. And then it goes up 2. So right there, we would have known that would have been the starting point of the transformed log function. And of course, the asymptote moved over 1, right? So it's going to start like that and go through there. And then we know the other point is down 1 over 2, down 1 over 2. So that's going to be there. So that's pretty much by graphing it, you know, the transform log, we could probably figure out those are where the 2 points are. But anyway, that's all. That's a good backup plan, is to graph both based upon transformations, and then also plug in the point to confirm it. So I'm not, this is already a long video. I'm not going to spend too much more time, but I hope you have the idea now that you can try values that make sense. Plug them in. For example, 2, for example, if I look at number 2, I think, hey, maybe I plugged in, I'd like to make the exponent 0, so I can make x -1, and then this would be what? This would be 1, 2 to the power of 0 minus 3. So easy problems. Also remember absolute value functions, that the value inside after whatever you plug in for x, if it's negative, it becomes positive, right? So remember that. Let's see what else. Log 2, we just did one of those. Radicals, remember what's inside has to be greater than, or the total result has to be greater than 0 or greater. So the biggest, smallest x could be would be -5, etc. Things like that. As you're graphing it, cube roots, remember you can have positive or negative in there. You could have x could be 1, right? That'd be a nice easy value. What else? Because I think you should know how to do pretty much most of these. So definitely make sure to get through 1 through 6 for sure, because there's going to be a problem on the test like that. And then after that, you can maybe keep going. But in this point, it's just to solve both algebraically as well. So, you know, that's good practice. Set these, you know, set these equal to each other, right? And then solve for x and get through as many as you can. And remember that the answers are on the back part of it. My thought would be go ahead and try to at least do 1 through 6 and then maybe through 9. See if you can get through that, and then we can talk about that tomorrow. And hopefully that's enough. Make sure you guys work together and take good notes.